Welcome to the online narrated lectures for CM2101. In week 9 we will be discussing the use of a form of mathematics known as group theory to determine the symmetries of normal modes. The methodology is the same as you will have been using, or will use, in CM2111 to determine the symmetries of group orbitals. Indeed, the labels that you've been using in molecular orbital diagrams such as sigma and pi describe the symmetries of the molecular orbitals and are derived using group theory. For vibrations, knowing the symmetries allow us to determine what the vibrations look like, their selection rules, and together with knowledge of the effective force constant of the normal mode, can be used in the calculation of vibrational frequencies and thus predict the vibrational spectrum. Well, first we will look at the character table and identify the symmetries of normal modes with the symmetries of irreducible representations. Then we will look at the application of group theory to molecules and the use of group theory to determine reducible representations. We will look at how the reducible representation can be reduced to their irreducible components, and then how we can use the projection formula to determine what the vibrations look like. We will then look at the symmetries of vibrational states in order to determine which vibrations are infrared active. After discussing degenerate representations, we will look at the vibrations of ammonia. We will also discuss Cartesian displacement coordinates to identify vibrations in systems in which it is difficult to determine the internal coordinates. Then we will look at the symmetries of group vibrations, and finally we will look at the nomenclature used to label irreducible representations. In part 1 we will begin by looking at the character table and identifying the symmetries of normal modes with the symmetries of irreducible representations. One of the most powerful ways of dealing with normal modes of complex molecules is to classify them according to their symmetries. The activities of these modes can be judged with group theory using the character table of the molecular point group. Each point group has an associated character table. A set of character tables is given in the miscellaneous folder of the work bin on IVLE. The character table shown here is for the C2V point group, which is the point group for molecules such as water, formaldehyde and nitrobenzene. The first column lists the symbols of irreducible representations of the point group. In the C2V point group there are 4 irreducible representations: A1, A2, B1 and B2. The second part of the character table shows the character of each symmetry operator for each irreducible representation. And the third part of the character table gives the mathematical functions that can be used as basis functions for that particular irreducible representation. To illustrate character tables, let us consider the effect of the symmetry operations of the C2V point group on a water molecule. Looking down the z-axis onto the water molecule, we can observe the effect of the symmetry operations on an arbitrary point x, y, z. Under the sigma xz symmetry operation, the x and z coordinates are unchanged, but y is transformed into -y. Under the sigma yz symmetry operation, the y and z coordinates are unchanged, and x is transformed into -x. And under the C2 symmetry operation, the z coordinate is unchanged, but x and y are transformed into -x and -y respectively. The identity operation E does not alter any of the coordinates. We can tabulate the effect on the x-coordinate of the various operations in the following manner. The x-coordinate changes sign under the C2 and sigma yz symmetry operations, but is unchanged by the identity E and the sigma xz symmetry operations. This symmetry behavior is given the label B1. It is more clear why this is given the label B1 when we list the numbers that multiply x. The The set of numbers 1, minus 1, 1, minus 1 comprise what is known as the representation generated by the basis x under the C2V point group. They also comprise what is known as the character of symmetry species B1. We can also tabulate the effect on the y-coordinate. The y-coordinate changes sign under the operations C2 and sigma xz, but is unchanged by the identity E and sigma yz. The set of numbers 1, minus 1, minus 1, 1 comprise the representation generated by the basis y under the C2V point group. This symmetry behaviour is labelled B2. We can also tabulate the effect on the z-coordinate. The z-coordinate is unchanged under all symmetry operations E, C2, sigma xz and sigma yz. The set of numbers 1, 1, 1, 1 comprise the representation generated by the basis z under the C2V point group. This symmetry behaviour is given the label A1. This is known as the symmetric representation. For any point group there is a symmetric representation for which every element is associated with the number +1. Note that in the character table for the C2V point group, the basis functions x, y and z are placed in the rows associated with the B1, B2 and A1 representations respectively. These representations are 3 of the 4 possible irreducible representations in the character table for C2V. As a matter of notation, the number in row gamma, column R, is denoted chi gamma R and is called the character of the operation R in representation gamma. For instance, when we're talking about the A2 irreducible representation, so where gamma is equal to A2, and we're talking about the sigma V xz symmetry operation, so we're talking about when R is equal to the sigma V xz symmetry operation, then the character under A2 of the sigma V xz symmetry operation is -1. The vector xyz is included in the list of mathematical functions in the character table. Note that these span A1, B1 and B2 as we discovered by observing how these coordinates transformed under the symmetry operations of the point group. Also given in the list of mathematical functions are the rotations Rx, Ry and Rz. This tells us the symmetry of rotations under this point group. This is the end of part 1 of this week's online lecture. Please continue on to part 2.